We'll start off looking at the product rule again, just as a review. The product rule basically works by taking the derivatives of each of the components separately and multiplying it by the other function. So that's probably not the most eloquent way to say that, but if you take the derivative of a product of two functions, take the derivative of one function times the other function, and then add that to that function times the derivative of the other function. So if we have something like this, there's a couple ways to do this one, but if we want to use the product rule, we take the derivative of that x squared plus 1 factor, and then that becomes 2x, and multiply that by the square root of x, and then we take that x squared plus 1 and multiply it by the derivative of the square root of x, and so we get 1/2 x to the minus 1/2, and then we simplify it. And the first thing I did there was, of course, expand the parentheses, and then now I'm taking the fractional exponents and putting it back into radical form. So I'm doing this. I guess my rule of thumb is that if you're given a problem with radicals in it, you answer the problem with radicals. If you're given a problem with numerical exponents, then you answer the question in numerical exponents. But that's a very loose, style rule. That there's nothing requiring you to do that. And certainly, the second line here would be a perfectly good answer, in any case. And of course, you can make the argument you have one more step to do here to rationalize this square root in the denominator. At this point in the course, I'm not interested in you being worried about that at all. Okay, so either of those two last lines would work. So if I did rationalize it, that's the way it would come out. Yes?
I'd asked a version of this, but when we see something like this on a test, will the x plus 1 or x squared plus 1 and then the square root of x be listed out as originally the separate functions, or do we just assume that anything that's inside of parentheses is one function, anything that's outside is another function?
Actually, neither of them. You're just going to get the function, and it's going to be up to you to decide what rule to use and then how to break it up so it conforms to that rule. So the other way to do this one, if you didn't want to use the product rule, is what this alternate is that say, okay, I'm going to expand the parentheses and then convert the radical form into exponents, and then I'll take the derivative of that. That was a good segue, Rhoda.
Yeah.
Okay, so if I then expand this, I can get it to the same form, and you can see I have the same answer by two different routes. Now, if it were me, if you just handed me something and say find the derivative of this, I would have chosen the second method. Sometimes with some functions, like especially next semester when you get to e to the x and sine of x and those kinds of functions, the product rule is inescapable. There's nothing, there's no way around not using it. But generally, when you have polynomials and radicals and things of that sort, expanding them probably is as easy as anything, because that's a fairly reliable thing to do, right? You're not going to make too many mistakes expanding those parentheses. And then once you get something like this down here, whoops, I'm pointing the wrong spot. Once you get, I should say, this expression here, that's going to be a fairly reliable thing to take the derivative of as well. So my own personal opinion is the alternate here is a little bit easier. But since we're only dealing with polynomial, radical, and rational functions, we're going to learn the product rule by using these functions. You'll get to the point where there's no alternative, but for most things that involve polynomials, there's a couple ways to do it. Okay, so let me take you through one more example. And I think the first one I had as something for you to try last Monday, so I'll just go right through the solution there. You can expand that and actually end up with those several terms to take the derivative of, or you can use the product rule. And you can see I've taken the derivative of the first factor here and then multiplied it by the second factor. And then I took the first factor times the derivative of the second factor. And so then when you expand that, you can collect it all into one nice tidy polynomial. So you'd get exactly the same thing if you multiplied out that polynomial to begin with. This next one is a little bit longer, but it's the same method. You take the derivative of that first factor. This factor right here is just 1/2 x to the minus 1 times that second factor. And then you add that to the derivative of the second factor times that first factor. And so then from here it's a matter of expansion and collecting like terms. And you end up with with what looks like a polynomial with fractional exponents, and we can convert that into a radical form as well. Yes?
Not really understanding how the fractional exponents work. That's where I always get stuck on me.
Okay, and this is something you should go back and if you are having some difficulty, make sure you're really lock solid on this. Go back to your algebra book and try a couple examples. So when you have the square root of x, that's going to be the same as the fraction. If you have the cube root of x, that's going to be the same as x to the 1/3. If you have the square root of x cubed, that's going to be x to the 3/2. And of course, this is the same thing as the square root of x cubed. So those kinds of rules, go back to your algebra book and get. I'm going to assume that you have those things down pat. Yes?
Just a question. Isn't 1 over x, doesn't that go to, oh, never mind. No, over, right? To the last little negative x and then negative
This one here?
2, yeah. Did you, so you brought x up from the denominator and then you took the derivative of that. Is that how you got it?
Well, I'm taking the derivative, right. So I took the derivative of this as x to the minus 1.
Okay.
And so that's going to be negative x, and then subtract 1 from negative 1 and you get negative 2.
Okay.
Okay, so let's get into the quotient rule now. The quotient rule is when we're trying to take the derivative of a rational function, or any kind of ratio for that matter, and the numerator looks a little bit like the product rule, except instead of adding the two, those two products, the f prime times g minus f times g prime, we're going to subtract them. So here order is crucially important. Excuse me. On the product rule, it doesn't matter what order you do, just so long as you take the derivative of one times the original function, add it to the derivative of the other times the other original function. Here, having that f prime as being the first term, f prime g is the first term, and then you're subtracting f g prime, you have to remember to do it that way. Okay, otherwise you're going to end up with a negative derivative. Now the way that you might want to think about this is, what happens if you're taking the derivative of the function f divided by 1? So imagine putting in a 1 there. You have, this just reduces down to f prime times 1 minus f times 0, since the derivative of 1 is 0, over 1 squared. And so it gracefully goes into just inventing a ratio of, instead of just f over 1. So that may be a strategy for you to remember it. Otherwise, if you're just better at memorizing formulas outright, that's what you have to do. but that order is important. So let me run through a few examples, and what I'm going to do on this first one is I'm going to make the numerator green and the denominator red, so you can kind of see what's happening here. So I have two functions, and it's not important to assign the function's names. I'm just taking the one function divided by another function, and so when I apply my my rule, I'll take the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Okay, so you see where the red shows and the green shows where they came from, and then that's going to be all over that denominator squared. I know it's a lot to write down, so I'll give you a minute here. So what you have to do at this point then is to expand those parentheses and collect the like terms. So I'll do that, and I'll just resort back to all black since I'm mixing them all up, and then I get my final solution. And the reason why you want to go that far, of course, is to end up with with a simplified solution, but you at least want to combine these here because there's a chance that there's going to be something that you can cancel with the denominator. So it's not important to expand the square of the denominator. If you're going to be able to factor anything, it's going to show up as an x plus 1, as some factor there. But the numerator, who knows how those things rearrange, and so the thing to ask yourself about this is, can you factor this into x plus 1? There's no point in factoring it if you don't have to factor it, but if you want to cancel something, the question is x plus 1 a factor? And so hopefully you can see that that's not the case here. That's whether or not it's factorable is not as important as it doesn't factor into an x plus 1 factor. Okay, somebody had a question?
Sorry, I just want to make sure. So this one really is as simple as whatever is in my numerator is one function, and is my first one, and then whatever is in the denominator is the other function. Okay.
Yes, it's that simple, except that if you have functions that don't immediately look like this, you can form it into that. And what I mean by that is, let's say you have something that has a ratio and you're adding another, let's say, a polynomial to that, you can make a common denominator and combine it all so you get a ratio. But once you have the function in the form of a ratio, it's top and bottom, numerator, denominator, and just blindly apply the rule. Blindly, carefully apply the rule.
So the common denominator would be the second function?
Yes.
Okay.
Okay, let's go on to another example. Now here's one that that is deceptively simple, and it turns out that it's perhaps not deceptively simple, but it has one of these cases where we can actually cancel something out. So if I look at the derivative here, that first term, the derivative of 1 is 0, so I have a 0 times the denominator, and I'm going to subtract the 1 minus the derivative of the denominator, and so I get something that's relatively simple, and I have the square of the denominator as my new denominator, or the denominator of the derivative. Okay, so then I simplify all that out, and lo and behold, here it is. Okay, this is not a startlingly complex example, but if you notice, it kind of follows the pattern of what happens when you have 1 over x. If you take the derivative of that, the derivative of 1 over x was negative 1 over x squared. And so here you have this linear term, this x plus 1, and it drops straight through. Okay, so we'll take another one. Anybody recognize that function? That was on the test, right? That was that function. And I gave you the derivatives on that. But now you have the quotient rule, so you can calculate the derivatives yourself. Okay, so the way you do that is we expand the denominator, all right? And the reason why I'm going to expand the denominator is you don't really know what the derivative of x plus 2 squared is yet. When we have the chain rule, you'll know what it is. But the only thing we can really take the derivative of directly are polynomials at this point. So we're going to expand that. And so then we're ready to take our derivative, and so we take the derivative of the numerator, which is 2x, times the denominator, and then we're going to subtract the numerator, which is x squared, times the derivative of the denominator, and put that all over x plus 2, and then square that square, and you get to the fourth. Now notice I didn't retain that x squared plus 4x plus 4. You can if you want. But remember, there's going to perhaps be a step where we can simplify things. And so if we simplify things, we're going to be canceling factors, so you want it factored anyway. So you can bounce right back to that original form. Now this is just a little bit of experience on my part. You'll get the knack of this kind of stuff as well. There's nothing wrong with keeping the x squared plus 4x plus 4, but you're going to have to ask yourself, can that simplify a little bit later? So then when I expand the numerator, what I get is those terms still divided by x plus 2 to the fourth. And then when I collect my terms, I'm going to get 4x squared plus 8x over x squared plus 4. And so I'm going to now factor out the 4x. And then notice I end up with an x plus 2 as one of my factors. And so that cancels with that x plus 2 to the fourth. Excuse me. And I end up with a derivative 4x over x plus 2 cubed. And for those of you that remembered, that function was on the exam. That derivative was the derivative I gave you.
So it's better to expand it out like this, or it's not better to?
Well, what you want to do, certainly you have a valid expression for the derivative here. It's not simplified. So then the question is, what's the best way to simplify it? Well, with a polynomial, you just expand it and collect all the terms. So you end up with 4x squared plus 8x. And if you have kept the numerator or the denominator expanded to x squared plus 4x plus 4, you have to think, is there something that can be canceled there? So that's why I reverted back to the x plus 2 to the fourth, because that's the factorization of it. And so that's easy to recognize now that I can factor out a 4x and cancel one of those to get my final answer. Now there's always a question on the gateway is how far do you have to simplify it before you have an answer that I'll accept. And really from the standpoint of the gateway with a polynomial, I'd like to see you get to this point here. And if you can't, and if you don't identify its factorization, that's not a problem. I really just want you to collect similar terms when you're using this. Because computationally, this isn't that hard to deal with, even if you just hang with that. If that's the thing that you have to, stick a number in, that's not a difficult thing to do. Okay, so it's about time for you to try. And here's one that's similar to what I just did. I'll write the quotient rule on the board to remind you. So like that. Okay, so we have two ways to do this. Using the quotient rule, we expand that numerator, and so I take the derivative of x squared plus 2x plus 1 times x squared, and then I subtract the x squared plus 2x plus 1 times the derivative of x squared, which is 2x, and then I'm going to square the denominator, so I get an x to the fourth. And so when I then expand the numerator, I get all those terms, and I'm still over x to the fourth. And then I'll collect my terms, and I get negative 2x squared minus 2x over x to the fourth. But looking at that, it looks like I can factor this. And in fact, I can factor out a negative 2x. And so with this factorization, I can simplify it to be negative 2 times x plus 1 over x cubed. Okay?
Would we get points off if we left it as negative 2x times x plus 1 over x to the 4?
Not on the gateway, but on the exam you would. Okay? So on the exam, I'm going to ask you fewer things and expect you to do them a little bit more carefully. I know there's a time pressure with doing 10 derivatives. There, the gateway, I want to make absolutely sure that you're lock solid on the rules. I'm going to assume the algebra. Okay? Now, I said there was 2 ways to start with. Now, this is where we get into the territory of overuse of the quotient rule. Quotient rule, this is a perfectly valid, absolutely lock solid way to do it, but there's actually an easier way to do this particular one. If you expand that, now we have that single x squared in the denominator, and so we can separate this out into 3 fractions like this, and then that derivative is done fairly straightforward, right? What we do is we put that in that form where we have coefficient, variable, exponent, and so now our derivative is going to be negative 2x squared minus negative 2x to the minus, I'm not saying that right, 2x to the negative 2 power minus 2x to the negative 3rd power. And then if I rewrite that, and then I do the common denominator, lo and behold, I get exactly the same thing. So I think those are both practical simplifications. Certainly stopping at this point with this one is okay. And here this should be pretty obvious to cancel that x, but it's not wrong if you leave it there. If you fully simplify things and keep things as factors, you get exactly the same answer. So here's a very clear example where, depending on where you stop, you can get 2 functions that look a little different. But I think the second way is easier. Okay, so that's always a good question to ask. Now we couldn't do it with this the one that I did before. If I turn back a page, I couldn't do it here necessarily because what I have is the x plus 2 squared in the numerator. Now what I can do is I can put this up in the denominator. I can put this up in the numerator as x plus 2 to the negative 2 and then use the power rule. That's a perfectly legitimate use for that. But this one doesn't really lend itself to that as much as this one does, where this is clearly much easier to take the derivative of. Okay, so always ask yourself if you can rewrite the function into something easier to differentiate before you differentiate. And so here's an example of a complex fraction. You think, okay, you can jump right to the quotient rule to do this one, right? You can say, all right, the derivative of the numerator is going to be plus 1 over x squared, right? And then deal with all the consequences of that. But sometimes if you just make this a little bit more straightforward, you can get something that, I don't know, at least to me, I would consider myself a little bit more reliable in taking the derivative of this modified thing, even though we have a more complex, complicated denominator here. That I think that this is pretty straightforward like this, and then it's a matter of dealing with the polynomial in the numerator, expanding it, and then carrying on through that negative sign and simplifying it. So there we go. Now I'm pretty confident that this thing won't factor into anything that resembles x squared plus 5x, so I'm going to just leave it like that. Now when you're doing these things out, make sure you use plenty of space on your paper, and don't try and overdo it with expansions. Like, it's always tempting to say, I'm going to expand these two terms and apply the negative at the same time. And you know, I did it in 2 steps, but then I avoided writing down the step that got me to the simplification. I do this because I think I'm more reliable at conferring this double negative than to making sure that I get all my negatives right when I expand this and apply a negative to it. So you have to kind of find your own way around with it, but there's nothing wrong with writing out each step so you don't make a mistake. Obviously, on things that are supposed to cancel and get really simple, if you don't do the algebra right early on, you're going to end up with kind of a mess towards the end. Okay, then the other thing is what I put on the board when we were talking about doing some of the prior homework. Remember that when you have a coefficient in the front, that just rides along. Don't involve that unnecessarily. Yes?
What if you have a coefficient? What if it's dividing and you have a coefficient at the top?
Well, we have a couple examples here, okay? Okay, so here's one that we have. Is this what you're talking about, Alex?
Well, I was thinking like 4 over x.
Okay. Well, let's, I think I have one like that. But anyway, this one, don't use the quotient rule on that. That's overkill, right? Because you don't really have anything that has a substantial derivative on the denominator. The derivative of 6 is 0. So, you know, you're going to overcomplicate things. So if you rewrite this by factoring out the 1/6, now you have a polynomial that you can take the derivative of and just keep that 1/6 going along. And so we can take the derivative. It's going to be 1/6 times 2x plus 3. And if you want, then you can distribute back that 1/6, then you get 1/3 x plus 1/2. So really the substantial work, you know, if you want to look at where the real substance is, it's to recognize that rational function in the beginning is really just a polynomial with a coefficient that's distributed through it. The coefficient being 1/6. Okay, so here's a case where I have the 3/7 and I can just take out the 3/7, and then once I take out the 3/7 here, what then I notice is that I have just, you know, an x that can easily divide both of these terms. Now remember, divide both of the terms. Don't just cancel out, you know, the first term and leave the second term the way it is. But anyway, we get this function that's the equivalent function as that first one. And then, of course, we have the polynomial that we take a derivative of, and we get, lo and behold, 6/7, right? Because the derivative of 3 is 0. Derivative of negative 2x is negative 2. Negative 2 times negative 3/7 is 6/7. So you would never expect to see a constant coming out of that function, but rewriting it, you know, you get to the point where you actually do get a function that is easier to take the derivative of. So I guess kind of the moral of the story here is, you know, condition your your functions to make it easy to take the derivative of, all right? There's nothing that says you have to keep it in any particular form. You can use all the valid forms after that. So then here is I think I've shown you some version of this a few times now, where if you simply have a function to a power, in this case it's the square root of x, which is x to the 1/2, so it's x squared times x to the minus 1/2, we get x to the 3/2, and then we get 2x divided by the square root of x is 2x to the 1/2. And then you have 3 times x to the minus 1/2, and so we can take this and apply the power rule to it directly. And then I can rewrite it to be in radical form. I would not at this point go through and combine all those to try and get one ratio out of it. Certainly it's possible to find a common denominator and get some sort of rational function again. It's certainly not necessary. Unless you have a very specific reason to do it. I mean, it may be computationally simpler for you if you have to actually do a bunch of calculations. But this is certainly either of these two forms, this one where it's exponents, or this one where it's in radicals, I would consider acceptable answers. Do you have a question?
I was
Yes.
just wondering, real fast, on WebWorks, if you have to do a square root, how do you enter that again?
Well, the best way to do square root on that is just to use the SQRT in parentheses.
Does it have to be up?
I don't think it does.
It's lowercase.
Now, if you look in WebWork on the upper right-hand corner, there is a link that you can go to, and it'll tell you all the acceptable ways to put in things. Okay, so referring to that from time to time is probably a good idea. And there again, if you're confident that you got the right answer and it marks you wrong, send me a note on it, okay? I would much rather, make a few corrections or redirect you and say, hey, try it again, rather than beating your head against the wall for something that doesn't interpret your answer properly.
What about when it says your answer is the answer is equivalent to the answer you inputted?
Then-
There's no other way to write it. Every time.
Does it mark it wrong?
No, yeah, it marks it wrong. It tells me that the correct answer is equivalent to the one that I entered.
Oh, but it wants it in a different form?
And I tried putting it in a different form, and it still doesn't accept it.
Well, send that to me, because I'm interested to see what you came up with there, okay? All right.
I got a similar thing, except it said the answer's equivalent to the last answer I put in.
For me, that's meant that it was wrong.
Okay, so here are three of them that I'd like you to do. And, you can work with your neighbor, but I'd like you to really make an effort to try and make it all the way through all three of these. Let me go over these. We're running towards the end of class. So the first one, the straightaway application of the quotient rule. Okay, so you take the derivative of x times the denominator, and then you take the numerator times the derivative of the, and I got this one wrong, actually. Look at that. It was a little too late for me. Let me back up. And that was just 2x. Okay, it goes like that. And so the rest of my answer is going to be wrong, so I'm just going to write it out and erase it. I will correct it when I post it. Okay, so what I have to do, whoops, that's not my eraser. Okay, that's good enough for now, I suppose. Okay, the next one, do the same thing. And so this one comes out like that. And then there's one more level of simplification that I can make. And so there's my second one. Now the third one, you have to remember that you can factor out the 1 over the root 2. And so we have this polynomial. Now remember that pi is a constant, okay? You don't ever take, the derivative of pi squared is not 2 pi, okay? The derivative of pi squared is 0, but since it's a coefficient, it's just going to ride along, and so we get our derivative as that.